I'd like to welcome you all to our Biostat seminar series for this month. We're delighted to have Professor ADRIAN DOBRA here. It's kind of fortuitous. He was in Fort Lauderdale for the last couple of days attending an AI and statistics conference where he was one of the keynote speakers. So we kind of grabbed him on his way out to spend a little bit of time with us, meet some of the faculty in the division, and give us a talk at the same time. Adrian's got a very interesting background. He's got a bachelor's in mathematics, a master's in computer science, both from the University of Bucharest in Romania. And then in 2001, he got his PhD in statistics from Carnegie Mellon University. He's been at the University of Washington since 2006. He holds kind of dual appointments in the Department of Statistics and in the nursing school. Prior to that, he was at Duke University for 5 years, both as a postdoc in the National Institutes of Statistical Sciences and the SAMSI Institute, and then as a research assistant professor in the statistics group there as well. His research interests are quite varied. He likes to work on high-dimensional data analysis, stochastic computation and simulation methods, high-performance and distributed computing, graphical models and related graph theory, which is what we'll hear a little bit about today, categorical data analysis, multivariate survival analysis, and statistical genomics. So he covers a wide range of things, and it's a real pleasure to have him here today. So today he's going to tell us a little bit about multi-way Gaussian graphical models.
Today I will tell you a little bit about graphs, and well, this is an example of a graph, right? So you have a number of vertices, and then the vertices are connected through edges, right? So in this particular example, each vertex is associated with a state, and edges link states that share a border. Okay? So this would be a very simple way to summarize the spatial dependencies that exist among the states of the US, right? So the interpretation of that is that, say, for example, Florida has two neighbors. I think, well, okay, that's a geography test. So Georgia and Alabama, right? Okay, so I should have rehearsed that. Okay, so the interpretation of this graph can be taken to be that whatever happens in Florida is influenced or influence what's happening in the rest of the United States only through what's happening in these two states, right? So that is because, you see, if I were to follow the edges of this graph through vertices, then every time I want to get out of Florida and hit any other state, I would have to go through these two vertices right here that corresponds to Alabama and Georgia, right? So that's one idea of summarizing spatial dependence. Now, what I want to talk about today is the situation in which your data sets, your observed samples, are observed in each area of the United States. So you have the same variables observed in each state, and you would want to analyze all these data sets together by borrowing information. And well, you take these spatial dependencies into account, right? So this kind of setup appear very frequently in the analysis of aerial data, right? So there's nothing new about that. What is new is the fact that graphs can also be used to summarize dependencies, constraints we impose on model parameters. And those constraints will correspond with conditional independence relationship. What we don't know is how those conditional dependencies look like. That is something we are going to try to learn, right? So we'll have to deal with graphs we don't know, as opposed to those graphs we don't know and need to be inferred from the data. We have these other graphs that summarize spatial dependency, for example, and those graphs are known, right? So what we will try to do is put these two together in a coherent framework, right? So this graph, as it is shown here, doesn't necessarily have any apparent structure associated with it. However, there are ways to find structure in this graph. And these ways relate to graph theory. In this particular case, what I did here is I identified the 13 maximal prime subgraphs associated with the US graph. Conceptually, these maximal prime subgraphs are those subsets of vertices that involve edges and can no longer be broken into smaller pieces without losing information, right? So, for example, the first maximal prime subgraph, right, involves Alabama, Florida, and Georgia, right? So this is exactly the triangle down here, right? So I cannot break a triangle any further without breaking some of the edges, right? So the other prime subgraphs are relevant because you see you have this huge component right here that would somehow need to be accounted for jointly. See, since you can no longer break things up without losing any information. So looking back at graph theory, graph decompositions, create a way to summarize structure, and it can also give a very good way to give structure in the statistical model we fit to the data. Because now we can think about applying divide and conquer techniques in which we fit models separately in each component and then put them together, right? That would be one approach, right? So graph theory, it's really helpful in figuring out what's going on in graphical structure, like the ones we have here, right? So this is one of the examples I will be using today, right? So this is public data. So it involves mortality counts for 11 types of cancers in the 48 continental states plus DC, right? So our data will be a matrix, and this matrix is going to have a predefined row-wise structure of dependence that is given by this graph. That is the structure I need to account for at the row level. Now at the column level, you see, the column level I have types of cancers. So what I will be looking for is something like this, right? So what we are looking at here are choropleth maths of four common cancers, right? Colon, lung, breast, and prostate. You see that mortality rates, see, corresponding with each type of cancer separately, have spatial dependencies. Dark and lighter areas somehow go together, right? So what we will try to, and see this dependence involves that red graph we have been looking at so far, right? what we are trying to do now is figuring out what is the connection between these maps. How can we express dependence across cancers, right? And we will also do that by means of a graph that is unknown to us. So, for example, say we would only have these 4 types of cancers, right? So what we want to figure out is whether we have edges that link any pair of cancers. And what we will be looking for are how likely it is that some edges occur together. So we want to be looking at graphs and not edges separately, right? The interpretation of that would be as follows. So if an edge is missing, say, for example, if I determine I don't have an edge between colon and breast, that would mean that whatever is going on between colon and breast mortality rates are condition independent given the rest, right? So that's my goal. And we want to do that jointly. And doing it jointly is the key part, because you want to step out of the realm of regression, you see, in which you model the conditional dependencies, right? You want to know what's happening in your data jointly, because this way you can assure consistency. So for example, if you would be looking at what's happening with colon cancer in the presence of all the other variables with a regression, you can determine that, for example, breast can be relevant, right? But when you look the other way around, when you look at breast conditional on all the other types of cancers, you might not get colon cancer as being relevant. So there's an inconsistency that could arise from conditional models. And we want to propose a joint modeling framework, because if we do that, then we no longer have this kind of inconsistencies, right? So what we also want to keep in mind is how much data we have, right? So we effectively see if we want to treat all these data jointly, then all we'll have is one matrix. So that means we have a sample size of 1. So what does that tell us? Well, that tells us that we cannot be too certain in the choice of any particular graph. There will be a high uncertainty about which edges are present or absent together. So what we want to do at the end of the day is report that, because this is what is going on in the data given the information that we have. So those will be our goals. So let's see how to do that. So this talk will attempt to put together several bodies of literature that somehow have evolved separately. So one body of literature started with a paper by Dempster. So what Dempster did, it said, well, I have a multivariate normal distribution parameterized through the precision matrix